All right, so we're going to start our next chapter, which is our introduction to alcohols. The naming and nomenclature is pretty straightforward. You can either read about how to name alcohols in your textbook or watch the Khan Academy video I have posted. It's pretty straightforward and I don't think worth our class time. I'd rather focus our class time on learning mechanisms and reactions. All right, so really quick, let's review some acid-base chemistry. All right, and we've seen alcohols a bunch already, and in fact you even saw it in Gen Chem. The simplest alcohol is just water. And if you remember from Gen Chem, you saw an equilibrium constant where you can have two water molecules, and then there will be an equilibrium, and you can generate hydronium ion and the hydroxide anion. Which side of the equilibriums do you think is going to be favored, the left or the right? The left side, absolutely, right? And the reason for that is, if you remember back to first term, we said that the pKa of water is 15.7. The pKa of the competing conjugate acid over here is negative 1.7. That means that the hydronium ion is definitely the stronger acid. It's 15 orders of magnitude more acidic than water itself, which means the equilibrium is really going to favor the left-hand side. So in fact, let's show this using representative arrows. So water is the most classic alcohol. We'll be seeing it used a lot. However, more generically, you can have an alcohol that's connected to any sort of carbon group. The exception to that is you don't want this R group to be a CO double bond, because then what would it be? Be a carboxylic acid. So really it can't be a carbonyl. It does need to be some sort of simple alkane. All right, but same idea. If you treat this with water, actually let me show these individual bonds. If you treat this with water, you will get a reaction to some extent where water could act as a weak base, deprotonate your alcohol, and you could generate a new anion plus the hydronium. All right, just like before though, I'm going to leave this box empty and then we'll try to predict the equilibrium. And we know that the pKa of most acids is going to be in the range of about 9 to 18. Over here, our pKa of our corresponding conjugate acid is still negative 1.7. Nothing's changed. So which side of the equilibrium will be favored? The left-hand side, absolutely. So in fact, this looks a heck of a lot like the equilibrium reaction with water. All right, that's bringing us to some terminology. If we think about this anion up here, this is called hydroxide, right? We've seen it used in Gen Chem and in organic chemistry a lot. If we think about this anion down here, this is called an alkoxide anion. Does anybody know some examples of alkoxide anions that we've been using? Terbutoxide, right? So these can be either good bases or good nucleophiles depending on how sterically bulky they are. In general, though, you need a really strong base to form an alkoxide anion. Water's not going to really be strong enough to generate much of it. All right, does anybody know why there's such a huge range for pKa values for alcohols? I mean, that's like 9 orders of magnitude different. What could make it more acidic? So resonance, maybe there's some sort of resonance feature that could stabilize the anion over here. I think that's a great point. So resonance could change it. What else? Going way back to first term. What was that? Not necessarily hydrogen bonding, but maybe we have some sort of feature nearby that's pulling electron density away. What do we call that? Inductive effect or electronegativity, right? Electronegativity is generally used on the immediate atom. Inductive effects when you have an electronegative atom a few bonds away. So there's a few structural features that can change the pKa values of alcohols pretty dramatically. The most classic example is this alcohol, where again we could show this with water acting as a super duper weak base. Water could grab this proton, steal the proton, and we can generate an oxygen anion plus the hydronium cation. Just like before, we'll have this box where we try to predict the equilibrium. In this case, the pKa of our starting alcohol is about 10. This alcohol is called phenol. Does anybody know why it's called phenol? Because it's half a phenyl group, half an alcohol. Mush those two together, you got a phenol. There you go. And then if we think about the pKa of our hydronium ion, it's still going to be negative 1.7. So which side of the equilibrium is going to be favored? Left-hand side again. So we can plug this in. And then if we think about the name of this anion with the negative charge, this is called the phenoxide anion. And why is it unusually stable? Resonance, right? When you don't know the answer, you can always rely on resonance, but you can dump that negative charge onto 3 different carbons in that interior ring. So you could always practice that as a little bit of review for resonance. All right, so as you can see in all 3 of these examples, the equilibrium really favored the starting material side, indicating that it's hard to form these anions, whether or not it's the hydroxide anion, the alkoxide anion, or a phenoxide anion. So if we really want to form one of those anions, what do we got to do? Do we have to yell at it? Use a stronger base, I would say. Water in this case is a really crummy base. So let's talk about alkoxide ion formation. All right, so we must use a stronger base. All right, so there's a few different ways we could do this. One is, let's say we're working with something like ethanol, is treat it with a super duper strong base. So maybe we'll use sodium hydride. Sodium hydride's unique because we've got this hydride anion that is wickedly basic. It can steal a proton off of ethanol. We can form the ethoxide anion. Sodium is going to be the countercation, and what's our conjugate acid going to be? Hydrogen gas. This is really handy because this hydrogen gas is just going to bubble out of solution, which gives you a nice clean pot of sodium ethoxide. We could use this for elimination reactions, we can use it for substitution reactions, or we can use it for other purposes if needed. But this is how the ethoxide anion can be generated. However, it's not super common. I'll show you another option. Another option is to have an alcohol, we'll just stick with ethanol, and treat it with some sort of metal, an alkali earth metal in this example. So it could be lithium, sodium, or potassium. Those are generally the most common ones. These are really odd metals, and why do you think they're super reactive? Yeah, they're alkali metals. That means they have one valence electron that they really want to get rid of, right? So in this case, they're going to react with the hydrogen coming off the alcohol, and same idea. In this case, I'm just going to show this as a positive charge. This could be either lithium, it could be sodium, or it could be potassium. But same idea. We're going to generate half an equivalent of hydrogen gas. And then this will just bubble out of solution. This is typically what chemists do when they're trying to make something like sodium ethoxide, is they'll just physically take a brick of sodium, use a butter knife, and you can cut through sodium with a butter knife and just plop that into your ethanol and it will deprotonate your ethanol. Does anybody know why cesium's not used?
Because I can't even get some of that.
Because it'll blow up in your face, is the simple answer. Typically, the metals that we use are not the super duper reactive ones. Even with potassium, though, you have to be incredibly careful because potassium, if you plop it in with ethanol, it generates an enormous amount of heat, and you're also generating an enormous amount of hydrogen gas, which is a bad recipe, right? So with these, you have to be incredibly careful as you're forming them. All right, so I'll show you an example. So let's say you're a chemist and you need to prepare tert-butoxide. The easiest thing to do would just be to cut up some potassium. You could get shavings or just physically cut a small chunk and drop it into your beaker. And you'll get potassium tert-butoxide, which, like we saw before, is a nice non-nucleophilic base. We'll generate hydrogen gas that will bubble out of solution. Oftentimes, when you see potassium tert-butoxide used, you'll also see the solvent shown as well. So let me show this in context. Let's say I've got this starting material, and we see potassium tert-butoxide. Oftentimes underneath it, you'll see tert-butanol written out. Why do you think tert-butanol is often shown on the bottom? Yeah, it's a solvent. When you make tert-butoxide, usually you're not making 100% tert-butoxide, you're making a small portion of it. The remainder of that tert-butanol is still going to be floating around in solution, and it's just easier to make a mixture that way. So oftentimes you'll see the solvent listed underneath the reaction arrow. All right, I'll give you a second, but let's try to predict what the product would be for this reaction. And check with your neighbor. Are we going to get any SN2 here? Why not? It's not a good nucleophile, so this is a good base, but a bad nucleophile. All right, so that's one reason. The other reason I would say is we've got a tertiary carbon right there. There's no way it's going to fit in there and do any SN2 reactions. All right, do you think SN1 would work here? I don't think so. SN1 reactions, we have to have a bad nucleophile, right? In this case, this is a really reactive base. It's not likely that it's going to do SN1. What do you think is going to be favored here? E2, absolutely. So if we do E2 chemistry, we could get two different products, hypothetically, and then I want your help deciding which one's major and minor. Which one's going to be our major product? Left. So this would be our Hoffman product, and then this would be our minor Zaitsev product. So now we have the ability to actually make our reagent to do some of these reactions. Does that make sense? All right. We've actually seen a handful of ways of preparing alcohols too. So let's really quickly review the different ways we know for making alcohols. And then we'll cover some new ones this chapter too. All right, this is going back to last term. We saw how to make alcohols with substitution reactions. All right, so let's say I'm starting out with some sort of alkyl halide, and I need to pick a reagent to convert that alkyl halide to 1-propanol. The alcohol is shown on the right. What would be the most appropriate reagent here? Well, first of all, let's decide whether or not we think it's going to do SN1 or SN2. What do you think is more likely? SN2. Okay, so SN2, because this is primary, is probably going to be the best bet. All right, so I'll just make a little note of SN2 underneath. And SN2 reactions, we know we need a strong nucleophile. So a strong nucleophile should have a negative charge, right? So if we try to pick a reagent that has a negative charge, we probably want one with the hydroxide anion. So the simplest option here would just be get some sodium hydroxide off the shelf of your lab and then do an SN2 reaction. All right. Conversely, what about this alcohol? What reagent would we use here? Can we use sodium hydroxide? Why not? So sodium hydroxide can't do SN2 on this. Why? Yeah, it's tertiary down here. So because this is tertiary, no SN2 is possible. It's way too hindered. If we were to treat it with sodium hydroxide, what would happen? E2, right? So E2 would definitely be the winner here. We don't want E2. We want to make the alcohol. So what would be a better option? Yeah, just water. In fact, I would avoid using heat. Why is that? That would favor E1 elimination. We don't want E1 elimination here. However, we probably would get some anyways, just because it's really hard to control. And let's make a note of that. So we saw a lot of this last term. The key thing is remembering which reagent you need. It's really tempting to always pick hydroxide. However, we can't always use hydroxide because we might run into elimination chemistry. So we have to be very careful with the strength of our nucleophile. Any questions on this? All right. We saw a handful in chapter 9 as well with addition reactions. So we'll just write this down as a little bit of a review. All right, with addition reactions, we saw that we could generate alcohols a bunch of different ways. The first two made more substituted alcohols, and then the last one made our less substituted alcohol. All right, so the first one on the top, we could have done with water and some sort of catalytic acid. So that one's pretty easy. What's another option for getting your Markovnikov addition? Yeah, oxymercuration, demercuration. Followed by reduction with sodium borohydride. Would we really want to use these reagents for this reaction? No? Why? Yeah, it's not going to rearrange. So as a chemist, if I had one of my students say, I want to use mercury, I'd slap it out of their hands and I'd say, no, that's too dangerous. Use the easy one on top. Really, you would only use this one if you have a high risk of rearrangements. All right. And then the bottom one, how do we get the anti-Markovnikov alcohol? It's a two-stepper. Yeah, hydroboration oxidation. So we need a borane complex that can be borane with THF or any sort of ether. Sometimes you see ET2O, that's just another ether, diethyl ether. And then step 2, you need sodium hydroxide and then hydrogen peroxide. So all of these are review. The top two were Markovnikov. This bottom one down here was our anti-Markovnikov. All right, and then in addition to this, we saw methods for creating diols where we have two alcohols. So let's briefly review those. And again, we had three different ways of making diols here. We had two where we could make syn diols. And then another one where we could make an anti-diol. And for that lower example, we would also run into an enantiomer. All right, how can we make syn diols, meaning the top two? Yeah, KMNO4 was one option. However, we also need sodium hydroxide, and we need to run this cold. If you run this too hot, you'll actually over-oxidize it into a carboxylic acid, and we don't want that here. All right, the next one was the one where you might go blind if you use the reagent. Osmium tetroxide. Followed by sodium bisulfite and water in our second step. And then the last one was our anti-diol, and we need MCPBA. And then we need some sort of acid source, and we need water in our second step. The main difference with these is that these are syn diols, where down here we have an anti-diol. We don't use the term Markovnikov or anti-Markovnikov for these because we're adding two different addition groups rather than just one. Does that make sense? All right, so before we jump into new fancy pants reactions, I want to step back into Gen Chem a little bit because I'm not sure how many of you covered oxidation states in Gen Chem. Raise your hand if you covered oxidation states and oxidation numbers. All right, a few people might be rusty, and a few people might not have done it with organic molecules. So let's go back and briefly review some Gen Chem. I even do this in Chem 110. All right, reduction. How do we define a reduction reaction? We gain electrons versus an oxidation. Which loses electrons. If you remember your mnemonics, some people remember it from oil rig. So oxidation is loss, reduction is gain. Other people remember it from Leo the lion goes grr. Whichever one sticks with you, just try to remember those. All right. Oxidation state is different than formal charge, so I did want to briefly review that. They are kind of related though. All right, so let's say we have a molecule that we're looking at, and in this case, let's look at methanol as our molecule. The first thing I always do is I draw out the Lewis dot structure, and I go really old school, and I draw out all of my electrons. And you'll see why in a second. And I know this seems really tedious. Whoops, I forgot my second one there. But this helps when you're determining oxidation state. So if we were to look at any of the atoms in here, do any of them have a formal charge? No, but they do have oxidation states. So let's try to determine how we do that. So I'll show you a simple trick. First thing you do is you take the valence number for a particular atom in this molecule, and you subtract the circled electrons, and I'll show you which ones to circle. and that'll be your oxidation number. All right, and the key thing with this is when you're circling, the more electronegative atom takes all the electrons. All right, so let's focus on carbon for this first one. All right, so if we look at carbon, carbon's bonded to hydrogen and oxygen. And if we look up our electronegativity table, for example, down here, we can see that hydrogen is 2.1, carbon is 2.5. So it looks to me like carbon is more electronegative than the hydrogens, right? All right, conversely though, if we compare carbon to oxygen, we've got carbon here and oxygen here, oxygen's more electronegative than carbon. So now let's go back up and circle electrons around that carbon. In this case, carbon, like we said, is more electronegative than hydrogen, so it's going to steal those electrons from each hydrogen, but it's going to not get any of the electrons from the neighboring oxygen. Make sense? So now if we go to our little formula that I gave you, what's the valence number for carbon? 4. And then we would subtract our circled electrons, which is 6, which means the oxidation number for carbon and methanol would be -2. All right, let's try it really quick with oxygen too. We could do this for any element we want in here. So for oxygen, I'll let you try to figure this out, but I'll let you work with your neighbor on oxygen. Give me a thumbs up if you think you got oxygen. All right, so oxygen is clearly more electronegative than oxygen. We already determined that, and it's more electronegative than hydrogen. So it's actually going to steal all of the electrons. So for oxygen, the valence number is normally 6. Then we subtract the total number of circled electrons, which is 8. And the oxidation number for oxygen and methanol will also be -2. So even though they don't have any formal charges, we do need to account for their oxidation number or oxidation state. That becomes really important in organic chemistry. Does that make sense? I know in general chemistry, most classes tend to focus on inorganic species rather than organic ones, which is why I like to break it down this way for organic molecules. All right, let's do a few review problems. All right, in this first one, we're going to take ethylene, the simplest of all alkenes, and we're going to convert it to ethane. What reagent do I need? H2? Is that it? Yeah, it's some sort of metal catalyst. All right, what I want you to do now is to determine the oxidation number for each of the left-hand carbons, and then tell me how many electrons were transferred in this process and whether or not the process was a reduction or an oxidation. And I'll break it down to Chem 110 level down here. All the dots. All right, give me a thumbs up if you think you got the oxidation states. All right, I think we're on the right track. All right, let's zoom in on this molecule, the ethylene with all the dots. What's more electronegative, carbon or carbon? Carbon. All right, so we're going to split these. All right, if there's a tie, neither side's going to really win out there. All right, what's more electronegative, carbon or hydrogen? Carbon. All right, so if we do this, we can say, all right, circle all of these. And then down here, we know that the valence for carbon is normally 4. We're going to subtract the number of circled carbons, which in this case is going to be 6, which gives us an oxidation state of -2 for each carbon. Not just the entire system being -2. We know each carbon in this example will be -2. Down here, we do something similar. We know that carbon has a valence of 4. However, this time we only have 7 electrons circled, which means we're going to -3. All right, so let's zoom out on this big picture view. Did we gain or lose electrons? Gained. So each carbon gained 1 electron. Was carbon oxidized or reduced? Yeah, carbon was reduced. All right, what's the reducing agent? Yeah, that's the big thing people mix up, is that this is the reducing agent. It's the thing helping the carbon get reduced. What's the oxidizing agent? This is going to be our oxidizing agent. The entire molecule. Oops. All right, so it is a little bit weird. Students often see this reaction and they're like, but carbon's gaining hydrogen. Why is it called a reduction? And you have to take it all the way back to simple redox chemistry. In this case, each carbon's gaining 1 electron, net transfer of 2 electrons, and each carbon's being reduced. All right, I've got one other one I want to practice with, and then we'll call it good for the day. This is one that really fascinates me. So CO2, carbon dioxide, is a huge problem globally because of global warming, climate change, things like that. However, there's been a lot of work recently about pulling CO2 out of the air, because if we can potentially suck CO2 out of the air, we can mitigate some of the damage caused. And we could potentially even, hypothetically at least, reverse it a little bit. But the main thing is, well, what can we do with CO2? There's a few catalytic systems in place where you can actually pull CO2 out of the air and you can make methanol. The cool thing with methanol is methanol can be used either as a liquid fuel, it can be used to make plastics, it can be used in a huge number of commercial processes. So if we could pull CO2 out of the air and turn it into something useful, that's a game changer. The problem is these catalysts typically aren't super hot and require a lot of energy in order to do this, and we'll see why in a second. What I want you to do is to determine whether or not this was an oxidation or a reduction reaction and how many electrons had to be transferred in order for this reaction to occur, and focus on carbon. By the way, if you can invent a catalyst that will do this with ambient air and do it at a high enough scale, you will be an instant billionaire, if not trillionaire. So I would encourage you to work on that. What's that?
I mean, yeah, that'd be cool.
Yeah. No.
So do you guys know where they actually have tried doing this?
Canada.
So they've done it in the Netherlands. It doesn't work very well yet. The other places in the United States, they've actually tried these experimental catalysts on the flue stacks for natural gas plants, because you have a high concentration of CO2 versus a really small one. But again, it's really easy to poison those catalysts and then they die on you. So really what chemists are working on is making catalysts that are rugged and catalysts that will pull CO2 out of just normal air, not high concentration CO2 air. So pretty interesting chemistry going on. All right, did anybody figure out number one? A few people? All right, so really quick, we can go ahead and we can draw the Lewis dot structure for CO2. Old school. What's the oxidation number for carbon? We know it's normally 4 for its valence. So it would be 4 minus 0 would be 4, positive 4 in this case. All right, and then we know when we go to methanol, in fact, we already did this up above. What's the oxidation number for methanol? Would be 4 minus 6 would be negative 2. So did we gain or lose electrons in this process? Gained. How many electrons did we gain?
6.
Reduction. And we gained 6 electrons. That's why this process is so hard. Is simple redox chemistry where you're moving 2 electrons, that's not too bad. Trying to move 6 electrons around, you need something really, really powerful in order to make this happen. That's why this chemistry isn't as easy as people think it is. But I think that's where we'll end today. Your problem of the day is related to this, where I ask you to determine oxidation states on a handful of compounds and carbons.